So it's my great pleasure to introduce Chang-Shou Lin from the TIDA Institute and National Taiwan University. I think I think that he's really a great mathematician, and I think that his career is an indication of really the golden age that we're in now in mathematics. He started out in geometric PDE, and he's proved some wonderful theorems. You should go back and look at a few of them. But now he's mining this very rich vein which connects many parts of mathematics, and we're going to hear about it right now. So, Professor Lin.
Okay. Thanks for the introduction, and I want to thank committee to invite me to give a talk here. So, yeah, today I will talk about some part of my recent research. The theme of my recent research is the study the interaction of linear equation and the nonlinear equation. So of course, we may benefit the nonlinear equation from the study of linear equation, but the reverse, we also want to use the nonlinear equation to prove some result of the linear equation. So the object in the linear part, for example, is the so-called generalized Lamé equation. So the generalized Lamé equation is a Fuchs type ODE of second order. And so this second order is defined in the torus. And the torus is this for any period in the upper half plane. The nonlinear equation, classical, there is a theory by the Hermann and the Schwarz. So by using their result in the 19th century, the Lamé equation can associate two kinds of the nonlinear equation. One is the KdV. So this KdV is related to the potential is the periodic potential. And the other kind of the connection nonlinear equation from this linear equation is in the conformal geometry. So this equation is a so-called curvature equation. But with the matrix with conic singularity. In my lecture, this equation I call the mean field equation. But you know the this OD is actually in the complex variable. So for any of this kind of the OD, we associate a monodromy representation. So for the monodromy representation, we can talk about the isomorphism. Then this is naturally related to the Painleve equation 6. Okay, so so this is my recent work to study this equation through this nonlinear equation and see what's their relation. Of course, we can extend this linear part now is only second order, so we can study the 4 higher order. But for higher order, in general, we don't have the Hermite-Schwarz theory, but still we have some linear and nonlinear interaction. So, for example, in geometry and the analysis here, then relate to the so-called total system. So total system with the group is the SU n plus 1. So this is a type of AN and also BN, CN, and the G2 at least. So this total system actually in classical algebraic geometry is just the Pricker formula only. For higher order, then of course in KTV theory they can have the higher order associated with higher order linear OD, but I'm not so sure how to connect them in this case. But for the monodromy part, of course, we can generalize the Painleve equation to higher rank. So there is a possibility, and now is we may interested in the study generalized of the Painleve equation for any type of Painleve equation. Okay, so this is my introduction. So today I only talk about the how to apply the Painleve equation to some analysis problem. So first let me tell you my notation. Okay. So here, okay. So in my talk, I always use the W0 is the lattice point, omega 1 and omega 2 is tau, and omega 3 1 plus tau. And this is the lattice, and this is torus for all tau in the upper half plane. And we use the E tau 2. This means all the lattice point and half periods. Okay. And let me recall the classical Weierstrass elliptic function. So we have a pay function, and the zeta function, and the sigma function. So this is a well-known function. So let me just write the definition here. Pay is defined by summation all the lattice point, and the zeta function, derivative of zeta function, just the minus pay, and this is R function, but not doubly periodic. So, but actually is the quasi-period. We can define the eta I tau by this relationship. So first, let me tell you one example of my application to the from the Painleve equation. So let me consider two. You know, this is eta is the quasi-period, and the ek tau is the pay function. Take the value at a half period omega k divided by 2. Okay, so ek and the eta 1 tau are all basic quantity in the elliptic function theory. And so now I want to consider this summation of all them together. So this function is holomorphic in H, but never a modular form for any congruent group, because generally speaking, E1 is EK is weight 2, and eta 1 of course is not the modular form. But if you count the weight, eta 1 is weight 1. So this together never a modular form for any group. That means this sum do not satisfy any transformation law. However, we can prove the following result. So we consider gamma 2 is the subset of the SL2Z, and the mod 2 is the identity matrix. So this means AD is odd and the BC is even. So I can consider any fundamental domain of the gamma 2. Then I can prove EK tau plus E1 tau in any fundamental domain, there is exact one solution. So this kind of theorem, like this function has the is kind of the modular form, but actually it's not. So I'm not expert of the elliptic function, so I search for the literature. I cannot find any where to mention this kind of result. So this result seems new. And how to prove this this theorem? Actually, we can one of the main step of the proof, we have to apply the so-called Painleve property of solution to the Painleve equation to prove this result. So from the statement here, you can see Painleve property is very useful to study holomorphic function or monomorphic function function property defined in the upper half plane. So my talk is I will first give you some motivation. My original motivation, this comes from the Green function, deformation of Green function in the upper half plane. And study the critical point of this Green function. Then I will introduce a hyperelliptic curve, and then for those hyperelliptic curves, I will introduce a modular form. Then in the part 1, I will give some the proof of some theorem for the simplest case. And using the result here, we can count all the real root, and actually any root of the Eisenstein series of weight 1. And then I will go to more general case of modular form, and then I tell you what's the briefly discuss what's the Painleve VI equation, and then I will talking about how to apply the Painleve equation to function properties. So let me recall the Green function on torus is defined by the Laplacian. This is the Dirac measure, and the E tau, this is the area of the E tau. So my original motivation is to study the solution of the following linear problem. So this is the Green function. If I take A with each component in the torus, and I want to study the critical point of AI is satisfy this equation. So this NL is integer, is known, and this is half periods. Okay, so I want to study this equation to see the solution set, how to change it when tau is deforming in the upper half plane. So obviously, this equation 1.2, any solution of this actually is a critical point of the Green function on product of the E tau. So the Green function is written in this way. Okay, so summation all of them together, and the Gi minus Gj. This is the single part corresponding distance. So let me give you an example. So the simple example is n equal 1, just 1 only. Okay, if only 1, then the left-hand side here is just 0, and this reduces the critical point of the Green function. And we know Green function is an even function. That's G minus G equals Gg. So Green automatically, Green function has singularity at critical point at all the half period. So any Green function has at least 3 critical points in any torus. And then we call a critical point A is say non-trivial if A is not in the half period. So naturally, we want to ask how many non-trivial critical points of the Green function in any torus E tau. So this question was answered several years ago by Wang and myself. So this is the result is for each tau, the Green function G has at the most 1 pair of non-trivial critical points, plus minus A. This pair coming from this is even function. Okay, so this is the okay, so the net is naturally we will ask the following question when tau deform in the upper half plane. So first we ask may a non-trivial critical point at tau equal tau 0 suddenly disappear or suddenly appear? So second question is where the bifurcation might occur at some critical point. And then we want to understand the geometry of those tau such that Green function has non-trivial critical point. So we prove the following theory is first case A is never happen. And the B, bifurcation of the critical point can occur only at a half period. So for non-trivial critical point, they never a bifurcation point. So to answer the question 3, we call this omega 5 is all the tau has non-trivial critical point. So I quotient SL2G. And we also define omega 3 is similar. No non-trivial critical point. This is omega 3. And the result is the theorem 1.3 is both omega 5 and the interior of omega 3 are simply connected. And the boundary is a smooth curve diffeomorphism to S1. So here is the okay. So here is the graph to tell this is numerical simulation to tell us what's the torus has the non-trivial critical points. So for analysis, it's better we work on the fundamental domain of the gamma 02. So this F0 is tau is real part is between 0, 1 and the outside of the circle radial half, center at half. So here is the fundamental domain F0 is between this line and this line, and there is a circle here. Okay, so the outside in this region, and the fundamental domain of SL2G is just this one. So F0 is 3 times bigger of the fundamental domain of S2G. Okay, I want to tell you is in this tau in this F0 those tau whose Green function has 5 critical points, I want to prove actually it's bounded by 3 curves. Okay. Yes.
Could you say again what the difference between omega 5 and omega 3? What is the subscript denote?
Okay. So omega 5 is defined by has a non-trivial critical point. So this means the Green function has 5 critical points. And the omega 3 is the torus. Green function has no non-trivial critical point. So this means Green function has 3 half period, 3 critical point only. Okay. So now I want to, so this is the graph. So I want to prove that if tau in this fundamental domain, the set of tau has Green function has 5 critical points is lie on the is bounded by this curve and this curve and this curve. So what's this 3 curve? This 3 curve is defined by the half period omega k divided by 2. This half period is degenerate as a critical point of the Green function. This means the second derivative of the g at this point determine equal 0. So I have the 3 curves together. Okay. So the numerical shows each curve actually is unbounded. Okay, unbounded, and the smooth curve and connected. So there are only one component for this is the curve, and any 2 of them did not intersection. So this means for any tau, degenerate point has at the most 1 point because they don't intersection. So this I will prove this later at the end of the first lecture. Okay. So I want to extend this for general situation. Unfortunately, the equation we are working on is not an algebraic equation. Actually, this system equation is not all algebraic.
Was that a determinant equation?
No, it's not.
Which equation?
Okay, let me tell you. This equation. This equation, yeah. This equation. This equation is not an algebraic equation. Okay, but actually, we can decompose. We can decompose this equation into 2 parts. One is the algebraic part, and one is the non-algebraic part. And the algebraic part give us a hyperelliptic curve, and this hyperelliptic curve actually is identical with the spatial curve for the 3-bit Verdier potential. This is R, not N, this typo, in the KTV theory. So, so let me denote the hyperelliptic curve by Yn, and I want to tell you is like n equal 1, all the branch points of the Yn are solution of this non-algebraic curve, non-algebraic solution. I will tell you what the equation is, and we call a point there is a non-trivial solution if A is not branch point. Geometrically, this single non-algebraic equation turns out it gives us very important information. This is the global monodromy data for some linear ODE. Okay, so this is very important. In that case, we prove using this theory, we can prove no non-trivial solution could appear suddenly when tau deforms in H. And the second question is where is bifurcation can happen? This is much harder. So we conjecture is except for a finite set of tau in F0, the bifurcation point of this critical point can only happen at the branch point. So this problem actually is the set equivalent of the following thing. So supposedly you get you have two Bi, P1 and P2, and we consider Raman equation. Suppose both of Bi has the unitary monodromy representation, then this conjecture equivalent inequality here for any compact set outside of S, they always assume positive. The two parameter, different two parameter always has a low bound. So let me tell you the case of the n equal 2, solution of the 1.2. So this is what I want to tell you later. So let me give you first. Okay. So you see, this is also the F0, the fundamental domain of gamma 2. And the F0 actually divided by 10 curve. Okay? And the number here means in this region, non-trivial solution only have one. So from the picture here, I will tell you what the curve it is. Later I will tell you. And for example, in this numerical simulation, there are at most two non-critical, non-trivial solutions. So this means for tau here, there are at most there are exactly 9 solutions of the critical of the Green function. I mean equation 1.2. So I will show you how I will prove this at the end of the second lecture. So let me go back to the. So next, I want to tell you the hyperelliptic curve, how to come from the equation. Okay, let me assume the simple case is all the components equal 0 except 1. So this we reduce this simple thing. Okay, so easy to see. This solution is the critical point of the Green function defined in this way. Okay. Now the single Green function, the derivative Green function can be written in terms of virtual elliptic function, and you can compute it. Actually, this is equal zeta minus eta g tau. So how to define this? This is defined if z equal r plus s tau. For r is real, then eta, this is equal r times eta 1 tau plus s eta 2 tau. So from here you see this function is not holomorphic function in terms of z because eta is defined this way. Okay, so so the equation, the previous equation, so this is the equation we want to study, 2.1. And this equation would equivalent to two equations together. This one of equation is zeta function satisfy this, and another is Green function. So this first equation actually is the algebraic equation. If you apply the additional theorem for pay function, and this is not the algebraic. As I told you, this equation gives hypergeometric structure, and this gives monodromy data for some linear equation. Okay, so let me call all the solution. Call this yn tau is all the component is in the e tau, and all the ai satisfy this equation. Then I quotient by permutation group. Okay, then I call this yn tau. I tell you the theorem. So this theorem tells us yn tau actually is a hyperelliptic curve. So this means the existence of a polynomial with a rational coefficient with G2, G3, G2, G3 is a coefficient of the elliptic curve. Okay, and the B, how to define B? We define B in this way. So this is B. Given A point here, I define B here. And then I define C in this way. Then I can prove C squared equal LBB. Ln is some polynomial. So this polynomial degree 2n plus 1. And we can prove except for a finite set tau, this hyperelliptic curve is smooth. Then I want to tell you what the branch point is. Branch point of this set actually is the, if you consider as a set A1 up to n, so this equal, you put everything negative here. Not branch point means this set intersection is empty. And the important thing is yn tau, the closure actually just at one point to this hyperelliptic curve. Okay? So let me tell you, for branch point, because in this property, so either sum of A1, AN is AI is in the half period, then gradient equals 0. Or plus minus appear in AI, then this also cancel out. Therefore, any branch point must satisfy this equation. Must satisfy this equation. So for any branch point in the yn tau, already satisfy this and this equation. Hence, satisfy our equation of the 2.1. Okay. Sorry. So this is the 2.1. Okay. So this I told you. This is the. Okay. So any branch point is solution of 2.1. So by 1 is because the polynomial is degree 2n plus 1, so they are at least, they are exactly 2n plus 1 distinct branch point if this hyperelliptic is smooth. Okay, so let me tell you the example. N equal 1 is trivial. This is n equal 2. N equal 2, there are 5 branch points. So is 3 is come from the half period. First component is 1 and the second component another 1. And the 2 point, another is q plus minus q plus and the q minus minus q minus. Such q is satisfied this equation, okay? And then as n equal 1, I will study whether those points is the degenerate critical point of the Green function on this space. And similar, I can define a degenerate curve. Okay, so here is the picture I already tell you. For example, so this line, this C, okay, this is the C23 is very, you cannot see it. Actually, C23 is some line is something like that. Okay, so C23 is one of the degenerate line, and each C23 we have 2 components. Actually, is another one is here. So for example, you see C minus is this curve. Okay, and the C plus is this curve and this curve together. So totally is a 10 curve from the degenerate curve, and we want to prove each in any subregion of the divided subregion of F0 divided by those curves. The number of solutions, non-trivial, is the one we write here. So I will tell you this later. Okay, so the one important is all the degenerate curve is smooth and unbounded. So this property is very important. Here, I will show you Painleve property is essential to prove this. Okay, let me tell you, I only have let me tell you the proof of the first part using the modular form to study the curve. Okay, so I want to show you what I want to show you. Let me go back to the graph. I want to show you here is the omega 5 is exactly this domain. Okay, bounded by 3 curves together. So what it means? Okay, so let me consider the derivative of the Green function. So this is a Green function. And the fixed RS, I can define this together. Okay, of course, in our Green function theory, we only RS is real. But in general, we can define this RS is complex. Okay, I will tell you why this will appear in some content. So by quasi periodic, we know that if each one plus an integer, they are the same. But the minus, then get the minus. So hence, if RS is real, we might assume R in the 0, 1, S in the 0 and 1/2. Okay? And we see if this RS is real, now as a function of tau, this function, holomorphic function in upper half plane. And if RS is half-half, or 0 plus integer, of course, and plus 0, I mean RS in the, if RS in the half integer, then always manage completely, okay? And the important thing is the modularity property. If you change the tau by modular transformation by SL2G, and you define RS and R prime S in this way, then there is this modular form of the weight 1 appear. Okay. So from this property, we see when RS is a n torsion point, then this form actually is a modular form weight 1 with respect to gamma. And this modular form first discovered by Heck on a paper 1926. So I read some book about a modular form, but didn't see anyone mention this modular except at the book by Chang-Shou Lin. There he called the form as the Heck form. Okay. Furthermore, in a paper next year of the 26th, Heck noticed this Heck form actually is Einstein series of weight 1 if RS is rational, is an n torsion point. So let me recall the Einstein series is defined by in this way. This is -1, this typo. And the summation is run over all the mod n with K1, K2 fixed. Okay? And it's known this function is a monomorphic function in S, but holomorphic at S0. Then if you put S0, then you get we call this the Eisenstein series weight 1. And the Heck proof G, actually Heck form is a proportion to the Eisenstein series weight 1. Okay, but from the definition you see, if RS is a real number, not a rational number, Eisenstein series 1 cannot be defined. So in a way, this is defined is extend the Eisenstein series to a variable, not a rational number. This is very important. Okay, so to prove what I said to you, I decompose RS, a rectangle, into 4 open triangulate. Then so I want to prove this is the so we have 3 curves, degenerate curve. So here is omega 5. Okay. So I want to prove this. So actually to prove this equivalent the statement of 2. So for any RS here, any point here, we say if GRS has a 0 at some point of F0, if only if there are no plus minus, just RS only. If only RS in this triangulate, Then if RS here, then no solution. In 3 parts, no solution. Only this part has a solution. And the 0 is unique in F0. So I want to show you the proof of this. So how to prove this? So first, we want to show GRS. This is not 0 for any tau, for tau in the boundary of F0 in the here. Okay, so first step. And the second step is show GRS tau not 0 for any boundary F0, I mean including 0, 1, infinity, 3 cusp point. If RS in the union or in the open triangulate. Okay, so I want to prove these two things. Okay, let me explain this. So here is F is defined. F is defined in this way. If I can prove for any RS inside of triangle, then because the 0 of the, if there is 0, then boundary cannot have any 0. So the 0 cannot escape from the boundary. So this means once you know one point of RS has a 0, then the whole the triangle, any RS in the triangle has a 0. If one point has no 0, then no point in here has 0. So this is the idea. Okay. So first, how to prove this property? This property is PDE result. This property equivalent to the PDE. This I tell you, this is called the mean field equation. Has no solution when E tau is a rectangle. So this means tau equal IB. So this result is equivalent to this. And for the other boundary, just using the Mobius transformation, we can, once you prove this in this line, no 0, then the other part is no 0. So this is related to the PDE result. And then for this one, you just compute asymptotic behavior. Okay, so you compute the asymptotic behavior when RS not in the boundary. And we can prove they are never managed. Okay, so once we prove this, then at the 1/6, for example, this point, we can prove 0, 1/6 tau has no 0. Because this is a very good exercise of additional theorem, we can prove they are never 0, first one. And similar, you can prove this never 0. So we get this point in the triangle 1 has no 0, and this point in the triangle 3 no 0, and this in here no 0. So all the RS in 3 triangles has no 0. So the only one have is the RS is the second triangle, because 1/3 and 1/3 this has 0. So this is where we only use the module form to prove this, because we see. Okay, to prove this, we just multiply all the 3 torsion points together. So this is a module form weight 4. And we know the only one module form weight 4, weight 8. And the 0 of this module form weight 8 it only exists at this particular one. Okay? And the 0 is a simple 0. So from all I said, we prove the result is the only. So we prove the result. The statement 2. Okay, and the statement 1 is if RS is real, is is a corollary of this one. Okay, so I only have a few minutes to tell you we can apply this to find Eisenstein series. So how to find Eisenstein series zeros? So we just multiply all the module form for the n torsion point. Okay, and then this is the module form of weight very big, the number of the Qn. And it's easy to write this module form by the discriminant function of the elliptic curve and some power with some polynomial in J. J is the invariant of the SL2G. Square appear because any zero of the product must has a double zero, so we have to put square here. Okay, so now we want to compute the polynomial, and first we want to know how many real root of this lnj. So here is the result. If we want to understand J is in R, only if real tau is 0 or real tau is half. But we already know real tau is 0 has no solution, hence we only consider this. Okay, but the non-trivial critical point A must lie on the Z is, this Z is E tau, so real line in the half, because E tau, when tau in this way, then E tau is symmetry on the real line. Uniqueness tells us the A must lie in the line. So we write A equal R plus tau, then you take the real part of A, just the R plus real. So real this is 1/2 by this, and this is R plus S times half. So this is real part, and you get a 2R plus 1. So this means if this is 0 for some real tau equal half, only if 2R plus S equal 1. Hence, we can use this to prove if I define all the rational points, n torsion points satisfy this, but between 1/3 to half, and the other is 0 to 1/3, then I can prove lnj has exactly so many real roots in the 0 to 11728, and the exact real root in the minus infinity, and no root at all at the 0 and here, if n greater than 5 and not 0. Okay, so the question is how to compute lnj. This is a very difficult question, even for very, very small n, because you see, we have the product. Product is very hard to compute. So it's better we can replace product by the sum. By the module form, if you do summation, then sometimes just cancel out. So how to do this? We will use the solution of Painleve equation 6, because as I will tell you, any zero of the Z, if some solution has a pole at the Z0. So secondly, any RS, if they different RS, then lambda solution has different pole. So summation of them together does not cancel out any pole. And this is a rational function in T. And by the information cost at T equals 0, 1, and infinity, then you can compute all the lnj. But still, this is very complicated to compute. I have computed n up to 11, and the number is very big. But good thing is the root of the lnj actually are algebraic number, but not algebraic integer. If not algebraic integer, okay, then number series say the correspondence tau, not j, tau. Tau is transcendental. So this our conjecture is if we can prove this polynomial is reducible, then by using the by using the Painleve VI, then we can prove the then we can, if this is irreducible, then we can use this form to show j is always not an algebraic integer. If n greater than 5, not equal 6, then we can prove the tau is transcendental. This is my, I think, okay, I'm not number serious, but I think this might be true. Okay, so I stop here. Thank you for your attention. Okay.
So can I just
Yes.
ask you, so the one PE input,
Yes.
can you just say again, you
Okay.
have the
Yes.
equation on the vertical
Yes.
box.
Yeah, on the rectangle.
Periodic.
Yes.
And then you're saying, so why does that nonlinear equation?
Okay. The nonlinear equation. So we have this function. Important is this function is holomorphic. Okay. So when Rs is some n torsion point, usually module form is discrete, right? One module form, rational points are discrete. Okay, and now if I can control the zero of this function, such that the zero never on all the boundary, okay, never on the boundary including cusp point. Then if you get a zero, and you can deform Rs from one torsion point to the other torsion point, right? Then the zero cannot escape. So important thing is to prove this function has no zero. If you know the Rs restrict some domain, okay. For example, as I told you, if Rs is in some triangle, then if you move there, then all the zero cannot escape. So this is a very important property. And I will show you for the application of Painleve equation, we have to prove this first. And how to prove this? There are two parts. One part is on the boundary. So on the boundary term, on the boundary, this line. On the boundary, we have shown this is not zero. This is PDE result. As I told you, this is equivalent to non-existence of the solution to some PDE. Okay, this is a mean field equation. And for the cusp, it's easy because you just have to compute the asymptotic limit. Once you know this, then it's clear. So the most important is to prove this is not zero on the boundary. And this is why PDE coming into with this kind of problem. Okay.